Sorry. Hi, everyone. Can you hear me well? So welcome for the second invited talk. So we are very, very happy to welcome Martin Albrecht, who is a professor in the Information Security Group and the director of the Cryptography Group at Royal Holloway University of London. Martin is interested in the hard mathematical problems underlying cryptography and also in the cryptanalysis of deployed cryptographic protocols and implementations. His recent work focuses on lattice-based cryptography and post-quantum cryptography, on block ciphers for algebraic platforms, and attacks on cryptographic protocols. He's also a contributor to the Sage mathematics software and many other open projects. In his talk, Martin will give an introduction to estimating the difficulty of breaking constructions in lattice-based cryptography and related problems. So please give him a warm welcome for his talk. Thank you.
All right. Thank you very much for the invitation and welcome to my talk about literally a Python script. So you're in for a ride. So what I want to do is I want to talk to you about like how do we go about solving mostly LWE-based cryptographic constructions. So what are the strategies that we use? Specifically, I will talk about the primal and the dual lattice attack, lattice reduction, and finding short vectors. And then if there's time at the end, I might kind of talk a little bit about like, but what about those quantum computers, which arguably motivate to a large extent why we care. And along the ways, I want to introduce this lattice estimator. So I want to highlight some limitations and also kind of how to use it, how to interpret it, and so on, because I'm told this is of great interest to some of you here. So let's get going. So roughly speaking, at the end of this talk, you should have an idea of what this slide means, right? So like this is like an output of this aforementioned Python script, and it kind of, you know, I put in Kyber, which 768, which I guess means something to you, and then like I do some rough estimate and do some other estimate, and some lines come out, and somehow that's something you copy paste into your paper to kind of avoid that section talking about, you know, like how hard are these parameters. All right. Let's talk about some computational problems. We start with the learning with errors problem. So there's a matrix A and there's a vector C. And I give you the guarantee that C is formed by multiplying A by some vector S, and then I'm adding some vector E. And the trick is that both S and E have small entries, right? And your job is to recover S given A and C. And so what do we mean by small entries? Because we're living mod Q, it's not really well defined. Well, really what we mean is think of these things over the integers and then consider them mod Q. So we're considering the kind of balanced representation of other elements mod Q. And in particular, the proper way of thinking about this is to think about the discrete Gaussian distribution, which looks something like the plot here on the slide. But that's very annoying to sample from, so hardly anybody does it. So instead, something that we maybe use is the binomial distribution. So you pick some random bits and you add them up, and then that gives you something that looks somewhat like a Gaussian. It's a binomial distribution, or you just pick some small uniform noise. And essentially, the literature assumes that all of these behave the same. You know, like there are some corner cases here and there where you need to be a little bit careful, but roughly speaking, what you care about is like, how big is this noise? And so here's like, again, I'm illustrating this using some output of this, this estimator. And then like what we care about is essentially the standard deviation of this distribution. And I'm sure you can construct some counterexamples what I'm claiming here, but roughly speaking, what you care about is the standard deviation of the distribution, assuming it's centered at 0. And we know that there's no loss in security if S follows the same distribution as E, right? So you can think of S and E as both kind of vectors following from some small Gaussian distribution or whatever the distribution of your choices. Right, and then so with that, we can construct our inputs, the Kyber 768. So it has a dimension, an LWE dimension, then it has a modulus Q. We pick error distribution, we pick a secret distribution. We tell her how many samples we want, and we keep a tag so we can remind ourselves what we just constructed. Now you might ask, I like to do entrue. How do I do entrue? And it's very easy. You implement it and you send us a patch. And in particular, we don't have an entrue parameters class at the moment. You can hack things together using LWE. I think like somebody just needs to kind of do a little bit of legwork of making a nice entrue parameters class, and then we can all enjoy the fruits of this work. All right, so we can construct some instances. We've talked about some distributions. So let's talk about how we actually go about solving this. So what we have is that C minus A times S is equal to E modulo Q. Right, that's by the definition of the LWE problem. So let's write that in matrix form and over the integers. So that means I multiply something by A, and then I multiply something by some Q, and then I get something small out. Right. So in particular, if I multiply from the right by this matrix Qi, A, and I, then and I add my C, I get E and S out, which is small. I like to put all of this in one matrix, and I just kind of end up with this matrix B here. And again, I can multiply this B from the right with some vector, and I get a vector out that is E, S, and 1. And by construction, E, S, and S have small entries, so we have a small vector. So there is an integer linear, in the integer linear span of this basis B, of this matrix B, there exists a short vector, a very short vector by construction. And indeed, it will be unusually short, and I will tell you what unusual means in a second. Right, so all we need to do is like construct such an integer matrix and then just find an integer linear combination. It gives me something very short, and I've broken LWE. So this is known as the unique shortest vector problem for QI lattices. So essentially, so QI lattices are these lattices that are essentially random stuff modulo Q. And we are asking to find an unusually short vector there. And you can, of course, think of a decision variant of this problem as well. You don't have to find the vector necessarily. It might even be hard to decide on if there is a short vector in the span, the integer span of the columns of this matrix B. All right, USVP. All right, there's another approach. So that was the primal approach. Little hint. Here's another approach. So again, we're starting from C is congruent to A times S plus E modulo Q, and S and E are short, and C is kind of uniform, maybe. So what we now want to do is we want to find a short vector, but now it's a short vector that simply satisfies when I multiply it from the left by A, I get a short vector VI out that is also short. So in particular, if I take the short vector multiplied by C, if I then spell out what is C, well, it's A times S plus E. What I end up with is V times S and U times E, right? And so I'm multiplying something short by something short, and I'm adding it to something else, which is a product of two short things. And by the logic of lattice-based cryptography, short by short is short, right? So we get something short out if the thing is indeed an LWE sample. If I happen to have C uniform, then multiplying something short by something uniform just gives me something uniform, right? So, so what we can do is if we have some short pairs and very short pairs, UI, VI, then with very few samples, I can decide on what I have in front of me is indeed an LWE instance or not. So there's a bit of a trade-off here. I can maybe sample longer UIs, VIs, and then I have to consider more of these outputs in order to distinguish, or I put more work into finding short vectors, and then I have to spend less time distinguishing. So I'm a bit cheeky here. I'm calling the short vectors problem for QI lattices. And the idea is, so I give you a basis like this, looks quite similar to the previous basis. I just transposed A. And all I ask you to do is find me many short, relatively short vectors in here, right? They don't have to be kind of unusually short. They don't have to be the shortest vectors, just like something that's kind of short. And where kind of short depends on S and E, because I want to distinguish like these products from uniform. And then this allows us to distinguish LWE. And if you can distinguish LWE, then you can also solve search LWE. Essentially, you guess a component, that either makes the instance uniform or preserves it as an LWE instance. You run your distinguisher, and if the distinguisher is like, yes, that's LWE, then you guess correctly, and you carry on. That's roughly how it works. Okay, so that's the approximate SVP approach. And then you can compose all of this together with some sort of combinatorics. I already kind of hinted at some. You guess some component of the secret, and then you run your distinguisher. And roughly speaking, by linearity, what you have a guessing stage, and then you have a lattice reduction stage. But things are linear, so give or take, these things compose additively rather than multiplicatively, right? You make some guesses and then you run some lattice reduction, but you don't need to run a new lattice reduction for each of your guesses, right? You do some pre and post processing. So that is kind of, we kind of like guessing in lattice-based cryptography because like things compose quite nicely this way. And then, so these were the high-level strategies. And now you can read some of the outputs of this estimator I gave me earlier. So plain USVP is literally this strategy that I've previously described of running this USVP. Then we're being a little bit cheeky and call BDD an instance where you essentially do the same thing as USVP, but you relax some parameters because it's morally equivalent to solving the BDD problem. And then you can chuck in some guessing. So that's what we call the primal hybrid approach. Then the cis approach or the dual approach is the approx SVP approach that I talked about. And again, you can optimize kind of how you chuck in your guessing in order to arrive kind of at some improved complexity. Now, again, you may have heard of the Matsov attack against kind of LWE. There was a recent improvement on some attacks on solving LWE parameters. And you might ask, so how do I estimate the Matsov attack? And then indeed, it's easy. I have implemented, I just need to submit the patch. But you can just look at the appendix of kind of this preprint and then just copy it over because we needed it. And this is a good point to mention, like in most research software, the things that are well implemented are the things that somebody needed for their paper, right? So everything else is a little bit of a wasteland, and the things that somebody needed for a paper, like they're somewhat developed. So if you need something for your paper, put it in the estimator, help everybody else out, make it polished. All right, so these are the two approaches, right? Primal and dual. Let's talk about lattice reduction. So a lattice is just that. So think of it as a basis, and now I'm considering all the integer linear combinations of my vectors, right? So instead of in a vector space that with a basis where I can do any rational combinations of my vectors or real combinations of my vectors, I'm only restricting myself to integer multiples, integral. And because that makes these things discrete, so discrete subgroups of Rn, and so things that are discrete, there is such a thing as smallest, right? And so in order to talk about what we mean by small, we need to define a certain kind of amount of invariance. And one of the things is the volume of the lattice. And that's the volume of its fundamental parallel pipette. And it doesn't matter which basis of a lattice you start off with, but the volume never changes, right? So you squeeze one corner, like it comes out in the other, right? So like the volume stays the same. And then there's a thing called the Gaussian heuristic, and that is essentially a statement about like, if you intersect two bodies in space, like how many points do you have contained in that intersection? And it's roughly kind of a division of the volumes of these points, right? So that's roughly what the Gaussian heuristic states. And now what you can do is you can take a Euclidean n-ball. That means, the things that have vector norm kind of bounded by some constant or by some value. And then you intersect it with the lattice, and that gives you an estimate for how long do I expect the shortest vector to be in this lattice, right? So if that ball is too small, then there is no vector this short in the lattice. There's no integer linear combination that gets me there. But if it's too large, then there's many. So from this, we can arrive at something called lambda 1, so or the first minimum of the lattice. And that is roughly the volume, the dth root of the volume with these dimension, and then something proportional to square root of d, right? So roughly 1 over volume to the power of 1 over d is the length of this kind of shortest vector in the lattice. So now I can tell you what I mean by unusually short. If we say that the lattice contains an unusually short vector, if it contains a vector that is significantly smaller than this, right, in some sense. Okay, so then a thing that you may remember from linear algebra is the Gram-Schmidt orthogonalization. And that will be a useful thing because there's nothing that we love more in lattice-based cryptography than drawing these plots of Gram-Schmidt profiles, of log Gram-Schmidt profiles. And so in order to draw that, I need to tell you what the Gram-Schmidt profile of a lattice is. That's the only use I'm going to make of this. I just want to draw some lines. So we look at, so BI star is the orthogonal projection of BI, which is the ith basis vector, orthogonal to the previous vectors. So the previous I vectors, orthogonal to B0 to BI minus 1. So informally, what this means, I'm looking at my ith basis vector and I'm taking out all the contributions in the previous directions, right? So all the direct contributions, the previous directions don't count. I'm projecting them away and I'm only thinking, what's the new contribution? And because these vectors are orthogonal, we have that the product of their norms is the volume of the lattice. And so in particular, with my kind of superior LaTeX skills, I give you this animation. All right, so we have these norms of these BI stars. We're going to take the logs of them because, you know, these things multiply up to the volume. And now we can take a basis and we can consider these Gram-Schmidt vectors. We can take their norms. We can take the logs of those and we can plot them. Right, and so here, this is what a Q-array lattice looks like, kind of when you put it in, because there's this vector of Qs, and then there's a vector of ones. Actually, this thing looks really boring. You have a bunch of Qs, they're already all orthogonal, and then you have a bunch of ones. And so you get log Q and you get 0. Like that is the input profile for our computation. It's like the input profile couldn't be more boring, right? And then we run LLL, the famous kind of lattice reduction algorithm that gives us exponentially long vectors, but makes our basis somewhat nice. And then what you end up with is like some sort of line. And what we know is that the area under this line is the same as the area under the previous line, because we know that the norms of these vectors multiply up to the volume. We're taking logs, so the sum of them adds up to the log volume. Okay, so we get this line. And indeed, like the area of lattice reduction, what it does, it starts with a line like this and says, wouldn't it be really nice if that line was something like this? And then we're going to spend exponentially a long time in order to make the line that looks like this to look like this. So make it a little bit more flat. And in particular, the geometric series assumption by Schnorr is that the shape after lattice reduction is a line, and it's the flatter, the stronger lattice reduction gets. Right, so that's kind of roughly how we model of if I run some lattice reduction algorithm and I invest a lot of energy and computational time into this, then I get a line still, but it's a bit flatter than if I invest less time. So I say lattice reduction. So let's talk about these lattice reduction algorithms. So the thing that really kind of pretty much partly because it was historically first, kind of is considered and implemented widely is the BKZ algorithm. And the way this algorithm works is that it relies on an oracle that finds shortest vectors in a lattice. And you might say, hang on, Martin, you're telling me in order to find short vectors in a lattice, I need to find short vectors in a lattice. But the trick is this is in a smaller dimension, right? So I say I have an oracle that finds short vectors in a lattice of up to dimension 100. And the BKZ algorithm uses that in order to find somewhat short vectors in larger dimensional lattices. And the oracle will be the expensive part, and essentially the bigger the dimension of this oracle, the better the quality of the output of the BKZ algorithm. So here I have a BKZ, I have an oracle in dimension 5. And so, I give my basis B0 to B4 to it and say, like, would you be so kind and please give me a shortest vector in this lattice? And then like the oracle complies and it gives me one. So I insert it into my basis and I do some post-processing to make sure I deal with linear dependencies. That is pretty too boring to spell out here. And then, you know, I now have a better vector as the B0. And now we move on, but we don't quite move on to B1 to B5. What we move on to is we're going to take these vectors and we're going to project them orthogonally to B0. That is, we're going to ignore all the contributions in the direction of B0, and we're going to consider that lattice. And that is a perfectly kind of fine lattice, even though it won't have integer coefficients. I'm still restricting to integer linear combinations of my input vectors. So it's a perfectly fine lattice. So what do? Well, I go back to my oracle and say like, look, I have a dimension 5 thing again. Could you please be so kind and give me a short vector in this lattice? The oracle complies and then inserts it. And we keep on going until we hit the end. At the end, we reduce the dimension. And then what do? We start again. And we keep on going, we keep on going, we keep on going until the thing doesn't change anymore. That's the entire algorithm, the BKZ algorithm. Okay. And then if you do that, then what you end up with is a vector that has norm roughly delta B to the power of D times and then the dth root of the volume of the lattice again. And this delta B depends on this beta, which is the block size of my oracle, right? And so this becomes smaller the bigger my dimension becomes. So I've kind of given you kind of some of these numbers here. So the case beta equals 2 roughly corresponds to LLL. So you may have seen this constant 1.0219 before. And then as I go up to beta equals 500, I get a smaller constant for delta beta, right? And so, and this is what the estimator gives you when you ask it for beta for a given block size 500. And then the slope under the geometric series assumption is roughly delta beta to the power of -2. And you can express the quality of the reduction as a multiple of the volume, which is something that is easy to compute. Or you can express it as a multiple of the shortest vector in the lattice. That's a second guarantee that the algorithm gives you. This vector will be not that much longer than the shortest vector in the lattice. But you might not know what the shortest vector in the lattice is, right? So for an LWE instance, you know, it's hard to distinguish if this thing is uniform or if it's from the LWE distribution. So it should be hard to really know what the shortest vector is in the lattice. But if you kind of like have an estimate, at least for lambda 1, then you have a guarantee of what the algorithm would output. That is, so roughly, if you're in the cis or dual regime, then you care about the left-hand side of the slide. If you're in the BDD regime, in the primal attack regime, then you care about the right-hand side of the slide. But don't you worry, I will spell this out a little bit more now. So how does this thing behave? So this is BKZ 60. So 60 means this block size, and I'm running this in dimension 60. And the black line is based on the information I've given you. We're expecting a line. We know the slope. It's a function of this delta B. So let me just draw that. And then the red line is the actual output of running LLL on this particular input basis. And then, I kept telling you we go back and over about this again. We call this a tour. So after a bunch of tours, we indeed approach this line. And then I will talk about that difference in a second. Right. And all of this you can try at home. Just install Sage, which you should have installed at all times anyway. And then FPL is available in Sage already. Then there's G6K or Jessica, which is sieving. I will talk about that a bit more. And you can also use it in your browser. So it should be fairly easy to experiment with lattice reduction these days, hopefully. Okay, so when do you succeed? So what we have is we have some computational problems we would like to solve, and we have some algorithms that give us some guarantees. We haven't quite talked about how to realize this oracle. We will do that in a little bit. But for now, let's say we have this oracle. How do we know? How do we estimate when we can win? Because this is a talk about a Python script that estimates when we can win, so it needs to be able to do that. And the key observation for the primal attack is that so we start with the GSA, so that's the expected shape of lattice reduction after I finish my BKZ tour. And then I can also say well, I have an idea of what distribution this vector ES1 follows, right? So I have some estimate for kind of what the parameters of this error distribution is. So what if I start kind of projecting that orthogonally to essentially random vectors? So that just means I'm taking away contributions in one direction because this thing is meant to be spherical. And so it just means I can, in a well-controlled way, kind of take off dimensions. So I consider what will be the lengths of these projections. And now I'm looking at the index D minus beta. And the index d minus beta is exactly the index where the algorithm does the last big call to an oracle of dimension beta, right? So after that, the calls become smaller, they become a little bit useless. Before that, not everything of the lattice is in play. In this last call, everything is either projected away because it was at a smaller index, or it is considered by the oracle. And so now that means if I have my USVP instance, the projection of ESN1 is in the lattice that I'm considering for this very last block. It's in that projected sublattice. So, and I have an oracle that gives me the shortest vector in this projected sublattice. So if my projection is shorter than what I expect there to be if this was a random lattice, then my oracle has to return me the projection of the shortest vector. It doesn't give me the full vector. Everything is now projected orthogonally to a bunch of other crap, but I can now recover something that is a projection of an unusually short vector. And then it will be inserted in the basis there. And then it turns out just running LL recovers the full vector. So the success condition is that when the shape of this is such that when you have that crossover point, the projection is smaller than what you would expect BKZ to give you. And in that moment, BKZ gives you a projection of this unusually short vector, which gives you the unusually short vector. And this has been pretty extensively verified through experiments. So there were kind of even two papers about this, kind of like rechecking some of these conditions. And roughly speaking, this is how this thing actually behaves in practice. So we have a pretty good understanding of what we should expect from these algorithms when to succeed. Okay, so we now have a dual attack, and we know what norm it outputs because we know the guarantees of BKZ. And then we can just do some statistical arguments about like how many samples do we need to distinguish LWE from uniform. We have a success condition for the primal attack. So in that sense, we now know kind of how we would go about costing both of these attacks if we assume the oracle. There's one wrinkle I want to mention before moving on, how to find short vectors in a lattice, and that is that the GSA is a lie. So I told you we kind of like model this as this line, right? It's a nice line and you know the shape. And it's just like, that's just not what the BKZ algorithm outputs. It outputs a little kind of, we call this HKZ shape at the end. And in fact, they're kind of small wrinkles. So this thing isn't a line. Rather kind of, it kind of like is a curve that is somewhat close to a line in kind of most part of the lattice. So what you can do, instead of just kind of drawing the line based on this one parameter beta, you can run a BKZ simulator. So what this does, it just applies this Gaussian heuristic over and over again in order to estimate how would the shape be like. And then this is the green kind of plot here, kind of is the output of such an estimator. And this is from AsiaCrypt 2011 by Chen and Nguyen. And this does make a difference, right? So the GSA being a lie kind of does make a difference. In a world where we say like, is it roughly 100 or 150 bits of security, however we define that? Like, no, it doesn't make a difference. But in a world where we talk about, standardization and we care whether we hit that magic number of 140 operations or not, then it might make a difference of 5 bits. So if you can, the estimator, you can say like, assume the shape at the end is the GSA, the geometric series assumption. This is what we use when you say estimate rough, or actually run the simulator. So in this case, the CN11 simulator, this is what we use for an estimate. And just making that difference gives you a 5-bit difference in the cost of these algorithms. So if you're asking yourself, why does somebody else get different numbers? It might just be that they assume a different shape. Okay, so how do we put everything together? It's like, okay, so we have a number of tours and we call roughly our oracle d times per tour. So we have tau times d times our oracle, and then whatever the cost of our oracle is. we can maybe reduce this, right? In the tail, we're not actually kind of spending as much time. We might pre-process our bases, so these things might not actually be as hard as initially anticipated, or we can be a little bit cheeky and we just jump over a few blocks and see if we get away with that. We call this pump and jump in Jessica. And so, but like, you know, roughly speaking, tau times d times time of your SVP oracle is a good estimate for how long this will take. And so then the question is like, what do I put for tau? What do I put for tau times d? One thing to do is like, it has to do at least one, right? One call to the SVP oracle. This is what we call the core SVP estimate, and this is what estimate rough uses. And if you just run the general estimate, then kind of at some point, you know, in some experiment, I saw, yeah, 8 tours seems to be okay. So I put 8 there. So now it's tau equals 8. And so tau times d is the thing that we use for estimate, kind of when you don't do the rough estimate. And that makes a massive difference, right? So the difference between estimate rough and the like a more full one, like, is easily 20 bits, right? So like there's kind of an explanation of how different ways of thinking about this kind of like gives you quite different numbers. Okay, so now at this point, we can read the output, right? So this is what Primal BDD, as I told you, is this USVP with some relaxed parameters. And I'm telling it, please use the simulator. And then ROP is the elementary operations that we're using, our units. Then red is how much of that time did we spend in lattice reduction. Delta is this root Hermite factor that I mentioned. Beta is this block size, the size of my oracle. Eta is the dimension of the final core. I told you we kind of being a bit, you can relax some things about the last core that you're making. And D is the dimension of the lattice that we're reducing, right? So this is what kind of these outputs mean. Fascinating. That must be, yeah, but you can compute delta from beta. I don't know, did I copy it wrong? Software. All right. Okay, so how do I estimate SIS with the estimator? It's easy, implement it and send us a patch. It's actually implicitly implemented already because the dual approach, what we do is we're costing essentially SIS. How do I verify that this thing is actually correct? That's also very easy. Just check the code and send us patches. Okay, there's a final piece of the puzzle missing, and that is actually solving SVP, right? So we have this oracle, we assumed it has some sort of cost, and so like how expensive is that? So let me walk you through that. There is, okay, there's actually just one class of algorithms, sieving, but I like the other class of algorithms, so I'm also going to talk about enumeration. So let's agree for the purpose of this talk, there's two classes of algorithms to consider. One is enumeration and one is sieving. And so essentially enumeration is an exhaustive search. And it being an exhaustive search, it only requires polynomial memory, but it requires super exponential running time. So it runs in time, roughly beta to the log, times log beta. Sieving, on the other hand, is essentially a collision finding algorithm. And thus needs a lot of memory. You need a lot of samples to find your collisions in, not so dissimilar to the birthday paradox. And so it runs in exponential time, but also requires exponential memory. The way enumeration works is that you pick a radius. You say like, I'm going to pick like, you know, say it's the norm of the shortest vector in the basis because we know there's at least one vector in this basis that has this norm. And then what you're going to do is you're going to project your basis downward in the same way as we've done this before, right? So I'm now not going to consider, I'm going to go all the way down. I'm just going to consider one-dimensional. Everything's projected down to one dimension, right? So now I only have this be one star. And now I can walk in my integer linear combinations on this one-dimensional line, right? That's easy. It's just a one-dimensional line. I can walk forward and backward. And then for each of those points that I walk forward and backward, I can say like, how about I project back up, right? I lift back up, go to the next level and see how long is this thing. If this thing ends up outside of my radius, then it's no use and I throw it away. If it's within my radius, then I keep on going. So I do this for all my points and then I just keep the shortest one. That's the enumeration algorithm in probably less than a minute for you. How do you make this fast? Is you don't actually do a full enumeration. There's a little bit of, well, this corner of the search space, it's not gonna be there, is it? So the way you approach is like you actually cut down your search space so that your success probability is exponentially small, and then you run it on, re-randomize it and run it exponentially many times. But we have a super exponential algorithm here. So running it an exponential number of times might actually be beneficial. And indeed, this is significantly faster than just doing the full proper thing. The other thing is that this enumeration algorithm really depends on the quality of the input basis. So if I give you something that is already really nice and reduced, then finding a short vector is significantly faster than something that isn't nice and reduced. So the way you do this is recursively. So I have a BKZ algorithm and I want some implement some oracle in dimension beta. So what I'm actually going to do there, I'm going to run BKZ in this block with some smaller block size to pre-process it and then run my enumeration algorithm. And then when you put all of that together, then you end up with the blue dotted line. That's kind of the state of the art in terms of what you can get in performance for enumeration. And so, and this is just to highlight, like there's been some improvements over the last few years in terms of enumeration. So if you rely on an old paper with some old parameter sets, it might make sense to see kind of how those parameters stand up to current parameterizations. And so these are kind of fairly accurate predictions. So that if you run actual implementations, they will behave roughly with this performance. So there's not that much uncertainty here. How long does this run on a classical computer? Sieving, key idea. What I do, I take my basis and I sample an exponential number of vectors from this lattice, right? I just do essentially random integer linear combinations of my basis vectors and I put them in one big database. And then I'm simply comparing each pair and I'm saying like, well, if I subtract those two, do I get something shorter, right? So I compare these two. Actually, if I subtract those two, I get something shorter. So I do this pairwise comparison with everything and I end up with a new database of now shorter vectors. I again look at all pairs, I subtract them, and I keep the short ones, and so on. That's roughly the idea of sieving. And in order to analyze this, what you do is you say, like, let's pretend all my input vectors are on a sphere. They all have the same norm. And then it becomes a question of, like, what's the angle between two vectors that I need in order when I subtract them, I get something shorter. Turns out it's pi over 3. And so this is equivalent to saying if I have these two vectors on my unit sphere, take the inner product is larger than 1/2. And then kind of when you crunch the numbers, what you end up with, you need a database. The probability is something 2 to the 0.2175D. And so these are the number kind of like, that I have a collision. So I need at least this many vectors in my database, right? So I need kind of, because if I just sample them at random, kind of with a lot fewer of those, then I just won't have anything that is sufficiently close to reduce. So now I have this database of this size and I need to do the pairwise comparison. So that will be quadratic. So that would be the simplest algorithm, quadratic pairwise search. And so that's the complexity of the Gauss sieve is essentially the square of the size of this database, right? So you can improve this quite significantly, right? So far, what I've done is like, okay, let me just kind of look at everything and compare every vector with every other vector. But there's some vectors that are kind of close. It probably makes sense to check those. And there are some vectors that are really not close. So it doesn't make sense to check those. So what I do instead is I define buckets, which could just be the angle to kind of some random vector that I pick in space. And then for each vector that I sample, I just check in which bucket does it land, and I store it in that data structure. And then I do the pairwise comparison only within the bucket, right? So I have a structured search space. So in this case, the green area is the bucket that I define, and I will miss some candidates, right? But then you oversample your vectors a little bit, and then the fact that you're missing some candidates that are just on the boundary of a bucket doesn't really hurt you that much. So that's the strategy. So if V and C are somewhat close and W and C are somewhat close, then perhaps W and V are somewhat close, right? That's the idea. So what do? Put them in buckets, and then we have still a quadratic algorithm, but now on a much smaller space. So the two sieves that I'm mentioning here, because they are kind of widely implemented, will be BGJ. So that kind of does this strategy. And then BDGL, which is the state of the art, has a trick about how to decide which bucket you land in, right? Because if you just pick a random vector and say like things that are close to that, then you still have to check every bucket to see if a thing falls in there. But if you construct your buckets a bit more carefully, you can use some coding theory in order to decide without kind of, which bucket should I go to? That's the trick of BDGL. And all of this is implemented in a library called Jessica, which doesn't quite implement this Oracle view that I appealed to earlier, but instead kind of thinks of this database of evolving short vectors and moving them around. And then it implements kind of all of these sieves, these tricks and these sieves. And then in particular, so here is the average time for solving exact SVP on some laptop that I'm not kind of spelling out which one it is. And so the point of this slide is to convince you that the crossover between sieving and enumeration is in dimension 70, and it takes maybe 10 seconds, right? So as soon as you have a lattice computation that takes longer than 10 seconds on a laptop, then probably you want to do some sieving. The one caveat is it needs exponential memory. So, you can't just wait longer, right? So you might be in a situation, I just don't have that much RAM. So, but maybe, I have cores or I have time, right? So, but leaving that aside, which is a big aside, like the crossover is actually quite small. And then this is another illustration of this crossover. So the red dotted line tells you what would essentially, by our estimates, it costs to solve SVP exactly in the dimension D. And then there's a thing called the Darmstadt SVP challenge, which does not ask you to solve SVP, because it would be really hard for anybody else to verify, even for you to verify, that you actually have the A shortest vector in the lattice. It's easy to verify that this is a vector of this norm in the lattice, and we don't expect shorter vectors, but it's really hard to say like this is definitely, there's nothing shorter in here. So what it actually asks you to solve is the Hermite SVP, which is like expressing it in terms of this volume that I mentioned earlier, and then it gives you some wiggle room so to make sure that there definitely is a vector. So this is, and the green line plots what we expect this to cost. This is an easier problem, strictly an easier problem than SVP as indicated by those. And as you can see, this is from the Hall of Fame, like there was some enumeration-based algorithms kind of solving that, and then they were roughly kind of on the line of the expectation. But I need to stress what an engineering feat it was to hit that green line, right? So them agreeing with the green line does not in any way trivialize their work, because like actually doing that, scaling up to hit that green line is, a lot of tricks were needed. So then Jessica, a sieving algorithm comes along, and then like just is a lot faster, right? Because it's simply a faster approach to finding short vectors. This is the green dots. And then shortly after Jessica, which was for CPUs, Leo, Mark, and Wessel kind of did Jessica for GPUs. And I don't know how to compare the CPUs and GPUs, and I probably kind of show how ridiculous I am in front of this audience, not knowing how to compare those. But you can do this much better. So maybe the way kind of I would phrase it, they solved the Darmstadt SVP challenge in dimension 180, right? And previously we did dimension 155. And that was the max where we maxed out, and their table starts at 158, right? And this is something that scales exponentially. So this is a significant improvement. The way they do this is essentially they stream the database through the GPU and then use low precision inner products in order to make decisions on kind of, do we have a candidate here or not? Again, you can try this at home. You can try Jessica at home, or if you have a CUDA CPU, GPU, you can try the Jessica GPU. sorry, tensor 1. All right. Okay, so then on costing sieves, it's still a little bit open. Okay, so what is the actual cost? How do you scale this? Like, so you may have heard about like people discussing cost models. And so what this boils down to is, so we need exponential memory, and one way kind of to think about this is like, I'm just going to pretend memory access is free, right? And then like, that's an underestimate. But if you still hit your desired security level, then you don't care. Or when you start optimizing, say like, actually, I should account for this, right? Just reaching a random memory cell, an exponentially large memory, like this is not free. So we should account for that. So that's number one. Number two is, so you start modeling kind of these sieves, and then they have these coroutines, and they're like, oh, and then there's some sub-exponential crap. I'm not going to model how expensive that is. But maybe that sub-exponential crap actually is a significant contributor. Or maybe you have an improvement in that sub-exponential stuff that then makes the algorithm a lot faster. And so in particular, this Matzov paper, they have two contributions. One is kind of an extension of a dual attack that we mentioned earlier. And the other one is they first found a bug in our estimate for like some sub-exponential part of costing a sieving algorithm, and then gave a nicer algorithm that even after fixing the bug kind of improves that. So that's the kind of, it's how do you decode this random code, right? And then in a way, in the original BDGL paper, they just kind of, it's not the focus. They say like, we have to do this, but it's a sub-exponential algorithm. So for the headline figure of what's the cost of this algorithm, this doesn't matter. But they do this. And then when you compare this with like roughly speaking, the Kyber estimates are kind of are these kind of like pre-bug fix estimates. But if you do this, then you shave off like 7 bits of security, right? With that, just improving this lower order term. On the other hand, kind of a recent preprint by Leo is to say like, yeah, okay, but then kind of you're assuming that everything compounds nicely and then the probabilities work out. So, so you actually need to account for kind of probabilities of success in this regime that you're targeting, and that increases the cost again. So what I'm saying is that if somebody claims they give you within like 10 bits of security an estimate for what it costs to run a sieve in high dimension, then kind of I would like to read this kind of 50-page write-up where they account for all these details. So there you kind of probably want to be on the safe side and just slap another 20 bits on this until we figured out how to really cost these. And these are not really asymptotic algorithmic improvements that we're talking about, but it's really about understanding of what is the cost of the algorithm that we already have in a more precise way, right? And then we give you a bunch of cost models. So we say like, I believe this cost model, you can plug this into the estimate and say like, I'm gonna pretend that this is true. All right, so let me quickly talk about some quantum stuff. You can do both of these SVP things on a quantum computer too. So essentially, we need to find a pair that reduces. You can use a Grover search there. Enumeration, you can use Montanara's quantum backtracking algorithm for some quadratic speedups. And of course, the devil's in the detail. My flippant summary should not suggest that kind of this is actually that easy, but like this is the high-level idea. One of the problems that you have is like, why are the quantum attacks kind of not that much better? So the best algorithm that we know is sieving. And the problem is you now have an exponentially large input on which you sieve. So number one is like, whatever kind of improvement you have, like, sure, I can improve this quadratic part, this quadratic pairwise search. That's where I can slap my Grover on it. I still have to construct this database of exponential size. So that's number one. Number two is the search space is very structured, right? I talked about this bucketing idea before. So this quadratic search that Grover excels at improving is actually very small. So the buckets that you actually do the quadratic search in when you parameterize these algorithms, even in large dimensions, these are very small buckets. And so the quadratic Grover speedup, even the ideal one, is fairly small, like even in an ideal setting. And you can achieve essentially the quantum speedup for the most simple sieve, the Gauss sieve, you can achieve that classically by just using the structure of the search space. So that's one of the reasons why for sieving algorithms, we don't seem to have like that big improvements on a quantum computer. And then when you kind of start accounting for everything, including things like error correction, then like the gap between what a classical computer, in some cost model gives you and the quantum computer in some cost model gives you is fairly small. And it is fairly small, but there's a speed up, but roughly speaking, you don't need to care about the speed up. And so I guess you can fight me about the statement after the talk or maybe in the question. And so the reason is, so the standard way of comparing is to say like, all right, this thing should be at least as secure as A as lambda, right? Say maybe A as 128. And so Grover's algorithm, in an idealist model kind of cuts that to the 64 operations or Grover iterations, right? So what we're comparing on a classic computer, it should take something like 2 to the 128 operations, and on a quantum computer, it should like 2 to the 64 operations, however you define them. But the gap between sieving the quantum and the classical case is like so tiny that we have to increase the parameters to hit the 2 to the 128 in a classical setting. And then the quantum computers just don't get us anywhere near to the 264. So in that sense, like even if you have a 20-bit improvement to a quantum attack, it probably still doesn't mean that any parameters need to be updated, because like the gap, like how far the quantum improvement has to go until you actually hit that square root, which is what you're targeting, is a lot. So it's a frustrating thing for a crypt analyst. It's like, I have a quantum, let's pretend I have a quantum computer. There's very little I seem to be able to do on lattices in terms of like, I can't even get the quadratic speed up. Other approaches, there's a pure combinatorial approach, BKW. You can use Gribner basis, which makes me happy, but most of those, essentially in most regimes, you don't have to worry about them unless your secrets are small or you have a lot of samples, but we cost them for you in the estimator anyway. And I think that's it. Thank you very much.
Thanks a lot, Martin. Is there any question in the room for Martin?
A lot of that is really paradox.
Yeah, so we account for everything that the literature knows, which is surprisingly little. So like roughly speaking, the way we know how to solve ring LWE and module LWE is just thinking of this as an LWE instance and solving that. And you can get some improvements of maybe up to a factor n, which is the dimension, in some algorithms, because, as you mentioned, some rotations or something like that. And then a thing that is on the roadmap, but like just means like in some README, we say roadmap and then we list it, is things like overstretched n-true parameters or something like that.
Thank you. Any other question from the audience? Over there.
That's an excellent question. So you essentially need to hit the equivalent of the birthday paradox, right? So until you hit that, there's just nothing you can do with collision finding. The probabilities just drop kind of so fast. there exists some algorithms that wouldn't be that relevant in practice that actually do time memory trade-offs that parameterize between, it's essentially enumeration, polynomial memory is super exponential, and then exponential, both exponential. So these algorithms exist, but they actually build on kind of quite different ideas. And I haven't seen concrete estimates, but it seems like, like it's more like it can be done sort of thing.
Thank you. Another question?
So you talk about this, so you like use 20 days or more than us fact that there is classical quantum very there. So if you would say your next is like another is not on par, the more spirit, less spirit, or
Seems fine. I think there's difference between, right? So you're trying to roughly hit a security level. And then like what we're looking at is probably in the ballpark of plus minus 15 bits. And then, yeah, for hitting that, like, okay, right? If you want to hit like some magic number, then yeah, then, can you guarantee that you will stay above this magic number of like for the next 20 years? It's probably gonna be some improvement. Like, so I don't know. Yeah, I mean, like it's annoying, right? Because like maybe in 2 weeks somebody kind of has some cool new idea for sieving, but no, but it seems, like for what we know, like it seems like, at ballpark we have some good idea. There's some ideas, there's some evidence out there that kind of you probably can't do much better with known techniques. So there's limits on kind of how fast sieving can go. And it doesn't cover all the sieves that we know, but like, so it seems all right. Ballpark wise, I don't know.
Thanks.
So the final ones we have is
yeah, so yeah, I shouldn't have called them ring up. It's word operations. So think of this like a CPU instruction. That's kind of what we mean. But like if you're off by a factor of 5, then I say like, okay, we will fix this, but I will not eat chalk. So that's like, so ring operations for historic reasons, it really will mean like we're in a word model, and think of this as like, operating on integers of size kind of 32 or 64 bits, something like that.
So would that mean if you're in a BGV style situation where the underlying queue is huge, then you should really add a few bits because the queue is your word size?
Yes, but you can, I don't think the queue is going to kind of kill you that much, because you can probably do it partially of just considering the top of the basis when you do reductions. I think it's, you will have some overhead, and I know this is your long-standing challenge to us, like come back when you can solve LLL on BGV style lattice, which Paul Kirchner can do, by the way. But no jokes aside, like you can probably kind of by just saying like, I don't care what happens in the lower kind of dimensions, and then you take the transformation matrix, apply that, and repeatedly do that. So I think you can probably do this with at least integer machine arithmetic. The floating point ops is going to be a bigger problem. But that doesn't depend on Q, that depends on the dimension.
Okay, we may have time for a last quick question. Is it okay for the audience? Okay, then we can warmly thank the speaker again. Thank you, Martin. We have a track switch break, so if you need to change room, it's time.
Yeah, thank you very much. Yes.
Okay, so good afternoon. Welcome to the new post-quantum crypto systems session with two talks. And the first talk is given by Pierre-Alain Fouque.
Thank you, Jean-Sébastien. So I will present you BAT, which is a new post-quantum encryption scheme. This is a joint work with Paul Kirchner, Thomas Porn, and Yang Yu. So BAT is in fact a very compact version of Falcon, and so this is this kind of bird. So our initial goal was to provide, in fact, an encryption scheme as a companion to Falcon signature based on untrue. And so the main drawback of lattice-based encryption is the size of the ciphertext. And this has major consequences about the latency and the efficiency of TLS, for instance. So many studies express this concern. And for instance, the size of IP packet is 1,536 bytes. And so we need to, it will be better if we have an encryption scheme that fits into only one IP packet. So we start with Falcon because Falcon is a signature scheme such that the size of the signature, and the public key is among all the lattice signature schemes the smallest. However, Falcon has two drawbacks. So the first one is that it relies on floating point operation, and such operations are not available on all processors. That means that we need, in fact, to emulate them. And the second is that it's hard to protect against side channel attack. And so we try, in fact, to take the best of the Falcon and to remove these two drawbacks. So BAT avoid all of these two. So we do not need a floating point arithmetic, and it seems to be easier to protect. And the size of the ciphertext is, so for instance, we have two versions. So the first one fits into NIST level 1, and the size of the ciphertext is 473 bytes. And for the NIST 5 security level, so the size is a little bit more than 1,000 bytes. We also provide a lightweight version for about 80-bit security, and the size of the ciphertext can dramatically decrease up to 200 bytes. So you can see the future in the next slide that encryption and decryption are nearly fast, about the same as Kyber. However, we put all of the main computation in the keygen, and so that it's a little bit slow. So if we can compare that with all other lattice-based schemes. So you can see from N2 to round 5 different lattice-based schemes. And so among all of them, you can see that our performance are good, I think. Only the keygen is a little bit higher than all of the schemes. So we also compare with RSA and elliptic curve, in order to show you the difference. So the keygen is not too bad if we compare with RSA. However, if we compare with ECC, so the performance are not the same. So for the encapsulation and decryption, so the number of cycles are good. Okay, but in fact, it's not only Entrue and Falcon, and we need, in fact, to propose something new. And so I just remind you how works the decryption process in Entrue. So the public key is just division, the ratio between two very short polynomial, mod Q. And the secret key is, in fact, one of these two polynomial and the inverse of one of them, mod P. So P is what is called the masking modulus, and in fact, it will be easily used during the decryption. So to encrypt with Entrue a message M, so you sample some random R, and you compute P time H time R plus M mod Q. So to decrypt it, in fact, you just multiply by F, and you get C prime mod Q, and you can see that you have two parts. The first part that depends on P and G, and the second on F. And in fact, if some size conditions are satisfied, in fact, this equation holds over the integer, and so it's very easy to decrypt them. You just have to compute mod P, and then to inverse F mod P to recover M. However, in BAT, so we try, in fact, to use exactly the same secret key as in Falcon. And so the secret basis is a little bit more complex. So it involves, in fact, the two short vector G and F, and also capital G and capital F that satisfies some very particular relation. So this is very common to Falcon and to Mutaka, for instance. So to encrypt with this encryption scheme, you just multiply the message by the public key, and you add some random value. And then, in fact, you have to decode some ciphertext relative to the basis. So this is, in fact, BFG is a very short basis for Entrue. And more or less, in fact, you can see that to decrypt in the BAT ciphertext, in fact, what we exploit is that we have exactly one relation like the one in Entrue, but a similar equation also exists for capital F and capital G. And if we present this like this, so we have two linear equations, mod Q, in two different unknowns. And so we just have to solve this system. However, we are looking for a very short solution, mod Q. So this means that we need, in fact, to decode. And in fact, this is a very general problem. So we have C, and the public key H, and we need to recover S and E, which are very short vector. And what we expect for an efficient decoding is that all the operations are simple and efficient. And we also need that the decoding distance is large enough so that the security level will be good. So in fact, there is two different decoding in the literature. So the first one is by rounding. So it's very efficient and simple, but however, it cannot decode very large error. And the second one is the nearest plane algorithm, which can decode larger errors. However, the implementation requires high precision arithmetic. So for Falcon, in fact, so the size of the signature is in fact proportional to the maximum of the Gram-Schmidt norm. So this is more or less what Martin explained before. And but for BAT, in fact, we need to decode a large error in order to have a very good security level, and larger than in by rounding. And also, we want to implement all operation only in fixed point arithmetic. So all of the heavy computation has been moved in the keygen. And we also have a short optimization between the two distributions. So so the difference between Babai rounding and nearest plane algorithm is as follows. So you can see that with Babai rounding, you just multiply with some very short bases. You do some approximation and you just multiply by the basis. And in fact, the algorithm is correct as soon as, so we got two different relations between FE plus GS and capital E times S plus GS times S. So this is, in N2, you only have the first part, but for that, you also have the second part. For Falcon, in fact, is not capital F and capital G, is in fact the Gram-Schmidt orthogonalization. So it is capital F star and capital G star. So the good point for Falcon is that the size of GAS of the first vector and the second one are more or less the same. However, for that, so capital G and capital F are much larger, and this is not good for security. So we propose a new decoding algorithm. So it's very close to Falcon. However, we do not compute with high precision, in fact, the value V. That is, in fact, some so how much you have to remove from the first vector in order to orthogonalize this version. So it's more or less in 2 dimensions, so it's very easy to do the orthogonalization. And instead of having a very high precision to compute V, in fact, we compute V only Q prime. So we took only the most significant bit. And in fact, you can see that if Q prime is large, in fact, our value converges to the same value as in Falcon. So we also have so the second refinement is that in fact the size of E and S, so the distribution are not the same. So the size of S is very short and E is larger. And so in fact to have a better decoding in lattices, usually we like to have the same vector of about the same size. So we in fact rescale one of the vector with some tweaking parameter that we call gamma, and it's just in fact the ratio between the standard deviation of E and the standard deviation of S. So this parameter appear later in the description. So the encryption is as follows. We just compute H times S mod Q. So we divide, in fact, by K. I will go into this later. In fact, is because we do not rely on LWE, but in LWUR. So this is a rounding version of LWE, and it makes the scheme, in fact, more compact. So that's the main reason. So we do some computation, we compute some threshold, and if we are below the threshold, so we accept and we return the value. It's just, in fact, some one-time pad with random S, H of S. So to decode also, it's easy. We just use the previous algorithm that I described. We recompute the value, we compare with the threshold, we recompute the value C1, and if it's correct, if it's the same as the first one that we receive, in fact, we can decrypt and recover the message. So from this encryption and decryption scheme, which is in CPA, so we can, in fact, construct a key encapsulation method. And for this, we use a very recent paper that does this very efficiently with the security in the Quorum model. Okay, so the security rely on 2 different assumptions. So the first one is the untrue assumption. That means that if you get the public key, in fact, you cannot decide if it's a random value or if it's come from the ratio of two very short polynomial mod Q. So this is a very standard assumption for intrue and also scheme. So the second assumption is a ring WR assumption, and it means exactly the following. So I give you some sample A and also some value which is A times S mod Q divided by K, and also a rounding version of this. And you have, in fact, to recover S. So it's very similar to LWE, but in fact, you remove, we cut, in fact, the error at the end. So LWR, and it's a very common assumption. It maybe do not share exactly the same security guarantees that LWE, but it has been used in a previous scheme, and for implementation also it avoids the generation of random, and I think this is a good point. So the security parameters as follows. So we have, in fact, many parameters. So the first one is the dimension, so is n, and this is a power of 2. And the second one is Q prime, and as I said before, so Q prime is if it is large, so we G prime and capital F prime will be closer to the same value in Falcon. And this is, in fact, has some important, so the important is that it controls the decryption failure, which is also important for such scheme. So the other parameter are P and K that I used before. So K, in fact, is the decoding distance that we can have. And in fact, B is in fact very important because it is the size of each coefficient in the ciphertext. So we use this value, and we also estimate the security of our scheme. So we try to recovers secret key from the public key, and the second one is just to the key recovery of the message. So I give you two different values. So the first one is cost, in fact, the log of the cost, and the second one is the size of the block size of BKZ, because it's an easier parameter, and as Martin explained, so computing delta from beta is easy, but it's annoying. So usually we can to avoid this. So this is the size of our scheme for AT. So the first one is low weight BAT. And the second one are the two different schemes that achieve NIST level 1 and level 2. And so you can see that the size of the public key plus the ciphertext is reduced, and it's less than 1 IP packet. So here for the ciphertext, we count everything. We count the FO transform and all the headers. So this is the performance of our scheme. So I think we try to evaluate all parameters. So at the conclusion, so I present a new and true-based key encapsulation mechanism that we call BAT, because it's a little Falcon. It's very compact, more than all known lattice-based KEM. And the encapsulation and decapsulation is fast, similar to the one in Kyber. So all the operations that you need to use are very efficient, and only the keygen is expensive. And yes, maybe you can remember that BAT is very simple and fast for daily operation. And we do not need any fancy floating point operation. And we hope that all the implementation can be efficiently implemented with the side channel also. Thank you very much.
Are there any questions?
I don't know if you can count psych. So yeah, in the first slide, I think we compare it with psych here, and so you can see that. So maybe not so NIST level 1 and level 2, but low weight are about the same size. So, but maybe there is room for improvement. I don't know.
Any other questions? No more questions. So let's find the speaker again.
Sorry,
Yeah.
I didn't try.
So the second talk of the session is given by Melissa Azawi.
Hello, everybody. So this talk is joint work with my colleagues, Julia Kuzovkova, Tobias Schneider, and Christine van Vredendaal, and it's titled Post-Quantum Authenticated Encryption Against Chosen Ciphertext Side Channel Attacks. So first, a quick recap of the third round of the NIST post-quantum cryptography competition, although I think a lot of you are already very familiar with this. But yeah, we had 9 candidates left, and very recently NIST announced that Kyber will be the main camp to standardize, and then some of the schemes that are moving to the 4th round. But what's important for the rest of this presentation is that almost all of the camps in the competition use the Fujisake Okamoto transformation, or FO for short, to go from indistinguishability chosen plaintext attack secure public key encryption to an indistinguishability chosen ciphertext attack secure key encapsulation mechanism. And this indistinguishability CCA security is what we want to achieve for key encapsulation mechanisms. So the FO transformation is used for almost all of the camps because it's quite a simple transformation. And it's applied on the decapsulation, so where we actually use the secret key. So just to explain in the next few steps how the FO applies, so we have this input ciphertext here in blue, and then it goes into the decryption where we use the secret key to decrypt it into a message. And then to enforce the CCA security, what the FO camp does is that it will re-encrypt the resulting message using the public key into a new ciphertext, and then it checks that both of the ciphertexts are equal, so the received one and the re-encrypted one. And if this is the case, then we can move on with the rest of the key encapsulation, which is the key derivation of the key derivation function of the shared secret. Otherwise, we can reject implicitly or explicitly the ciphertext. So this is the way the FO transformation works. And of course, in the black box model, it's quite nice and it helps us to achieve CCA security. But it turns out then when we are in the gray box model, when side channel attacks are concerned, this transformation is actually an attack vector for chosen ciphertext side channel attacks. And I will explain in a bit how these attacks work. But the basic idea behind these attacks is that an adversary can craft or construct malicious ciphertext, which when decrypted, will depend on a small or an enumerable part of the secret key. So in the following slides, I'll explain just a few steps for the attack. It's a very simple version of these attacks, and there have been quite a few variants of it. So yeah, so this malicious adversary here on the right will craft this malicious ciphertext and send it to the decapsulator. The decapsulator will decrypt the ciphertext using their secret key. And it will result in this plain text or message, which is then not really the correct message, but it's a function of a small part of the secret key. Then, of course, since we use the FO in our KEM, this message gets re-encrypted using the public key. So all the intermediates in the FO transformation will depend on the message, which is then just a function of a small part of the secret key and also public data. So at the end, all the intermediates will just depend on this part of the secret key. So if we have this decapsulation running on an embedded device, that means that the leakage of this re-encryption of the FO transformation will give the attacker directly some information on the small part of the secret key. Then what they can do is just repeat this attack with different ciphertexts. And each ciphertext will basically help them to target a different part of the secret key. And at the end, they can just repeat the attack for all the parts of the secret key until they recover the full key. And these attacks are quite powerful, and there have been quite a few papers about this in the recent years on the different key encapsulation mechanisms, variants of it. So not exactly the one that I just described, but a different variant of it. And in particular, 2 of these are presented at CHESS this year. So yeah, so like I just mentioned, these attacks are very powerful. And what we can do to protect against them, since they're technically side channel attacks, is that we can use masking or high order masking, which is of course the most popular countermeasure against side channel attacks. And but unfortunately, at COSAE 2022, we showed that the leakage of the FO transformation implies an increase of 1 to 2 masking shares to achieve a target security level, which means in practice that this implies a slowdown factor ranging from 1.2 to 3, which is, well, it doesn't seem that big, but it's actually quite significant for embedded applications. So to motivate the work and also the rest of this presentation, we can take a closer look at the cost of the masked decapsulation. So in this table, what we describe is the cost of the masked, I don't know if the pointer works, oh, there it is. Of the masked decapsulation. And in particular, we just look at Kyber and also the subroutines of the decapsulation. And then the columns here correspond to a different number of shares. So what we see from this table is that actually the cost of the masked decryption is less than 8% of the total cost of the masked decapsulation. And the decryption is technically the main operation that we have to perform, which means that overall the cost of the masked decapsulation is completely dominated by the FO. So in practice, if we could find a way to get rid of it, then we save over 90% of the total cost of the decapsulation, which would be quite nice. But of course, we can't just remove the FO since we want CCA security. So the idea that we investigate in this work is actually very simple. It is to replace the FO transformation by signature verification over the ciphertext. So now the decapsulator will never decrypt any untrusted ciphertext or ciphertext for which the signature has not been verified. And the main advantage from this is that, of course, the signature verification only involves public data, and we don't require any side channel protection. So this type of construction is not new at all. It's actually been suggested over 20 years ago, and it was called either sign encryption. And in this context, we use the encrypt and sign paradigm for our construction. And in particular, at EuroCrypt 2002, it was shown by Ando Desan-Rabin that this construction achieves CCA security, but under some specific conditions. So the main theorem is that if the underlying encryption is indistinguishability CPA secure, and we also use a strong signature scheme or UFCMA signature scheme, then the encrypt and sign construction achieves CCA security in the outsider security model and UFCMA security only in the insider security model. Now I'll explain later in a few slides what the distinction is between outsider and insider security model. And what's relevant for us, since we are in this post-quantum setting where we want to use, of course, Kyber, it's been shown very recently by Chatterjee et al. That this construction also achieves CCA security in the post-quantum setting. So what do we use this encrypt and sign construction for? Is that we construct what we call an encrypt and sign chem as opposed to an FO chem. And the main idea is that the encapsulator would both encrypt a message, but also sign the ciphertext. And then the main advantage comes in the decapsulation, So in the decapsulation, we get rid of the FO, so we get rid of the encryption and also the ciphertext comparison, which are both quite expensive to mask. So now we just end up with the CPA only secure decryption, which is not what we want. And now we add the signature verification before the CPA decryption. So that way we never decrypt untrusted ciphertexts. So in the proof, at least in this paper from Eurocrypt, they show that encrypt and sign only achieves CCA security in the outsider security model. And the way they are defined is that outsider security means that the adversary cannot be a legitimate user of the system. So the adversary does not have a trusted sign-in key pair such that the decapsulator will verify the signature of their ciphertext and then decrypt it. So that's why it's quite intuitive why this encrypt and sign construction achieves CCA security in this model. On the other hand, insider security means that the adversary can be the sender. So the adversary has a trusted signing key pair and can sign ciphertext. So this last model is very strong, and also it there's not really room for using signature in this case, since we trust public keys from the adversary. But for the rest of the talk, of course, since the construction, the encrypt and sign construction or the encrypt and sign chem only achieve CCA security in the outsider security model. For the rest of the talk, we just focus on this setting. And it turns out that in practice, whether we need outsider or insider security, it's determined by the use case. So we just do not just assume that we need only outsider security. It's determined by the use case. So what we use our key encapsulation mechanism for. And one of the use cases where outsider security is enough, and also quite a crucial use case for embedded devices, are secure encrypted updates or secure encrypted update mechanism. So this diagram sort of gives a small example of how that would be implemented, but there's different ways to do this. So mainly we have this backend that provides the updates, but then before the device is deployed, we can also provision keys and certificates. For instance, we can provision the sign-in public key so that updates can be checked. So we can check the source of the updates and also the integrity of the updates. And if on top of that, at some point, so when the update is ready and it needs to be sent, if we want to also encrypt the updates, we can do a key exchange or key encapsulation mechanism to share symmetric key to encrypt the update. And what we suggest to do is that for this step to replace it, instead of using the FOChem, to use an encrypt and sign chem. And the way we ensure this outsider security is that now, since we provisioned the public key, the sign-in public key onto the device or the corresponding certificate, we can make sure that when we do our encrypt and sign chem, that the device never decrypts ciphertexts that do not come from any other source than the actual backend. So now we can take a look at the improvement from the encrypt and sign chem versus the FOChem. So in this table, again, we have the cost of the decapsulation for a different number of shares. For the Kyber decapsulation, and then the second and third column are for the encrypt and sign chem using the underlying public key encryption of Kyber. But then we use either dilithium or Falcon for the signature verification. So first, for a low number of shares, we achieve 80% of the cost of the decapsulation for the encrypt and sign chem with Kyber and dilithium, which is an okay improvement. Then for Falcon, since it has faster signature verification, we go down to 40%. But then as the number of shares increases, which means that the masking of the decapsulation and also of the FO transformation becomes more and more expensive. Of course, the signature verification doesn't need any masking. And then at the end, we end up with overall less than 10 to 9% of the cost of the decapsulation. So this is quite a significant performance improvement. But of course, a lot of nice things do not come for free. So before, when we just had the Kyber decapsulation, we only needed to send one ciphertext, which is around 1,000 bytes. And now we need to send one ciphertext along with its signature, which means that if we use Kyber and dilithium, that would mean around 4,000 bytes. And then with Falcon, we would need 2,000 bytes. So just to recap the main pros and cons of the encrypt and sign chem. So first, the main advantage is that in this use case, or at least when we only need outsider security, it's 8 to 12 times more efficient, depending on, of course, the choice of the signature scheme, and also the number of masking shares that we need to mask the decryption. And the main con, though, is that the ciphertext now is much larger. 2 to 4 times, depending on the choice of signature between dilithium or Falcon. And also the whole point of making this construction was to avoid this FO transformation side channel attack vector, which is what we do since we completely get rid of it. But now instead we introduce a signature verification, which is not a side channel attack vector, but instead it's quite a common fault injection attack vector. So next we look at this last con, so the impact that this has on our encrypted sign chem. So yeah, so we remove this side channel attack vector, but we introduce a fault injection attack vector. So on this slide, we look at what is the cost of protecting the FO transformation against side channel attacks versus the cost of protecting signature verification against fault attacks. And for that, we just extrapolate the cost based on a simple fault attack countermeasure, which is recomputation. So it's the standard countermeasure against fault attacks. And very, very simply put, recomputing M times protects us against M-1 faults. So on this plot, we have on the x-axis the number of shares. On the y-axis, the logarithm of the number of K-clock cycles spent on the decapsulation. And then the top blue line is for the standard FO-based decapsulation. And then the red and the green lines are for the encrypted sign chem using either dilithium or Falcon. And then the dashed lines correspond to a different number of recomputations over the signature verification. So to make sure that no fault has been injected. What we see from this is that as the number of shares increases, the cost of this recomputation over the signature verification is quite small compared to the cost of masking the FO. This is somewhat of an expected result because recomputing is just a linear overhead, whereas masking the FO transformation is then has a quadratic overhead. So it turns out that this last con is not so bad because now it turns out that protecting signature verification against faults is less challenging and costly than protecting the FO transformation against side channel attacks. And in this case, since we are trying to scrutinize this encrypted sign construction, we didn't even consider fault attack protection on the FO transformation, which would mean that it just keeps getting more expensive. So to conclude the talk, I'll just recap some of the contributions and also some future work. So the main point was that we suggest this very simple construction or solution that we call the encrypted sign chem, which is meant to achieve improved leakage resilience for post-quantum key encapsulation mechanisms for practical use cases that fit in this outsider security model, so that do not require outsider security. And what we show in the paper is that this encrypted sign chem significantly speeds up key encapsulation mechanisms and also reduces the attack surface for post-quantum secure encrypted updates. And for future work, we hope to find other applications that could benefit from this construction or maybe similar construction, either for IoT communications or also some protocols in banking applications. And also in this work, we use, of course, we combine Kyber and dilithium or Kyber and Falcon, but there was also a proposal in 2018 for a lattice-based post-quantum scheme that does both encryption and signature at the same time, which is called sign encryption. So we could also investigate that. It seems to be slower than the combination of Kyber and dilithium, but maybe there's some work to be done or some improvements for the encrypted sign chem. Thank you very much for your attention. If you have any questions.
Any questions?
Thanks for the time. So is that replace you will be introduced but if you use the schemes not
Sorry, can you repeat the question? The sound is very bad. Yeah, so that's what I mentioned at the end of the presentation. So, you know, when we compare the cost of protecting the FO against side channel versus the cost of protecting the signature against fault injection attacks. So the gap is large, of course, But then, yeah, that's what I said at the end. We didn't consider this fault protection on the FO transformation, but technically it would also be very necessary. So then that would just add another cost to the FO chem decapsulation, and then the encrypt and sign chem remains even better than.
Any other questions?
So the very mass implementation, which mass implementation is.
This one is from the CHES 2021, I think. It was called Masking Kyber. No, not the new one from this year, no.
Any other questions? No, so let's thank the speaker again. So now we have the coffee break.